Glaciers fed by summer storms flow between the tallest peaks of the Palomar Mountains. The dark rock of the wind-worn ranges is black against the dazzling white snowpack. Katabatic winds tear down the slopes and kick up blinding blizzards. Becerra's frozen north grew from layers of snow compressed year after year for untold millennia until the ice sheets became the dominant force in the present era of Dove's climate regime. Hello and welcome to Lands Unknown. In this Footnotes entry of the Speculative Atlas, we have an overview of the process I went through to build the physical geography of Dove, and some concepts to take into consideration for world builders engaging in their own projects. If you enjoy the video, I would appreciate a like and subscribe, and if you would like to support the channel and the continuation of the Speculative Atlas, you can leave a one-time donation on Ko-fi, or you can become a member on Ko-fi or Patreon. There are currently 3 different levels which offer benefits like behind-the-scenes updates, voting on appendix entries, and seeing videos before they're released. In this video, I have 3 footnotes. The first outlines the methods I use to build Dove. The second concerns modeling temperature on colder worlds. And the third addresses the concept of aridity and how we can apply aridity to a glacial period. If you haven't watched the first chapter of the Speculative Atlas detailing Dovian physical geography, then I recommend pausing this video and checking out chapter 1. All of the references and sources are at the end of the video. Before breaking out Photoshop or booting up G-plates, I set aside some time to brainstorm goals for the physical geography and sketch the land masses and geographical features of the present era. I'm going to share a list of those goals that I had for the physical geography of Dove. I wanted the present era set in a glacial period with tall north-south orogenies that would create equatorial ice fields to break apart biogeographic realms. A Tethys-like sea was non-negotiable because worlds with lower global average temperatures have less evaporation of ocean water, which leads to less precipitation. So a warm sea in the interior can mitigate that potential for aridity. The supercontinent had to be in the northern hemisphere with substantial land area over the pole to maximize glaciation. Another reason why I wanted to have the supercontinent in the northern hemisphere is so I could have an isolated equatorial subcontinent, Araucaria, in the southern hemisphere with a rain shadow to create those wet winter, dry summer AS climates in the tropics. And the rain shadow is really vital because wet winter climates need regional climatic dynamics in order to occur on an Earth-like planet. The subcontinent needed to have the interior highlands in order to create those CS climates, and a Himalayan-esque plateau on the equator was important to drive a monsoon that would bring winter rain to the AS regions. One of my major goals for the Speculative Atlas is to explore cultural change through geography on Dove, so including people and where they come from was something I considered from the start. I decided to have people develop on a separate subcontinent, which rifted from the equatorial subcontinent. These became Alea and Araucaria, respectively. This rifting is relevant to the speculative evolution element because Alea is where the Dovian pseudomammals develop into placental analogues. Meanwhile, Araucaria has the Dovian monotrematoforms. A related characteristic was to have those expansive island chains that connect the western and eastern halves of the supercontinent, so people are able to migrate around. There's the island chain that connects the tropical Ionaean Peninsula to the western peninsula of Araucaria, and there are also island chains coming off of northern Alea that connect to northeastern Zalea, as well as sweeping across the southern hemisphere to connect to southeastern Araucaria. Since I'm dealing with global average temperatures that's cooler than the pre-industrial average, I wanted to keep all of the orbital mechanics identical or similar to Earth so I could focus more on the rest of Dove's characteristics. To achieve these goals, it was important for me to do the legwork because worlds are never built in a day. It took me about 4 months of working evenings and weekends to go through all the steps that I used to create the project. I started doing early sketches in May of 2025, and that early work solidified my vision for the final arrangement of Dove's land masses and geographic features. Rough drafts with pen and pencil are quick to do, so iterating on them lets you try variations. It's a lot easier to plan it out in advance, rather than changing it after you've already done a lot of the later steps. Originally, I had the idea of including another subcontinent, Central Becerra, descending to the subtropics from the northern polar circle, but that didn't work out because of my plans for how people were going to migrate to Araucaria. I have a few sketches from a notebook here. In section A1, we can see the inception of the Kotar Mountains and Turungian Plateau. I was also playing with the orientation. In A2, you can see the slight tilt. The variation of the northern and southern ranges in A1 and the eventual blocking for the Aravanian highlands in A2 both move towards achieving the dry summer, wet winter climates. For section B, we can see the sketches honing in on the desired shape of the Taiki Sea and the land masses of eastern and western Bussera. And as a part of sketching, it's important to plan and diagram out your plate movement in advance, like I do at the bottom of the figure in section C. Thinking through these motions prior to digitally or manually constructing a tectonic history will make the process much smoother. It's only after I'm confident that my goals have been met do I begin the next step. G-Plates is a GIS, or Geographic Information System software, and it's designed for academic research by geographers, geologists, and other experts as a tool to reconstruct the history of plate tectonics. I want to share some resources for those of you who are considering G-Plates for your worlds, and recommend some alternatives as well. Since G-Plates is a specialist tool, it's not the most user-friendly software, but it is a great free tool that you can use to design your worlds. The Apple Pie from Scratch guide over at Worldbuilding Pasta has a detailed supplement outlining steps to create a geologic history with G-Plates. I highly recommend reviewing the post and the entry on constructing a plate tectonic history. The G-Plates team has even included the Worldbuilding Pasta blog as an educational resource to help new users with the software. For a demonstration of G-Plates, Artifexian recreates the Worldbuilding Pasta guide as a video series as a part of the World Builders log, which spans from episodes 10 to 20. Since G-Plates was introduced to the world-building scene at large, a world-building category has been added to the G-Plates community forum, where you can visit to troubleshoot with other world builders. As I said before, this is not the only way of creating a tectonic history for your world. There is a lot to recommend about it since you're working directly on a globe, but dedicating a few weeks of evenings and weekends to learning the program and struggling through a billion years of history may not be worth the time. Worldbuilding Pasta provides recommendations for mocking up a geologic history on a 2D surface, and Madeline James has an entire entry on her own guide, as well as a video on her YouTube channel that takes you through the process of modeling a geologic history in 2D by cutting out shapes and shifting them around on a piece of paper. There are limitations to the 2D model, since your world is a globe. To address this, I have bought a styrofoam sphere in the past from a craft store for previous projects, and cut out shapes from construction paper, broke out a compass, and moved my plates around the sphere. There are a decent number of options for creating the paleogeography of your world depending on your scope and desired resolution. By desired resolution, I'm referring to the amount of detail included in an element of the project. Here is an example of a Köppen-Geiger climate classification map layered on Google Earth. This map has a low resolution, based on 0.5 by 0.5 degree gridded temperature and precipitation data. Less detail on a global scale could help decrease the amount of work on your project, especially if you're only interested in a specific region, which is what I was doing when I developed Dove. The World Köppen-Geiger Climate Classification map is low resolution. I was not defining every transition or including smaller climate zones in the global map. We can see the comparison here between the world map and the regional map of Arukia in Figure 12, where the latter offers a lot more detail. After completing the regional map, I went back to update the global map as we can see in Figure 11b. Even then, because of the resolution, the ranges and some of the semi-arid areas of the Aravanian highlands, hills in the southern rainforest, and valleys in the eastern peninsula coming off the Thuringian Plateau are not visible in the world map. At some point in the future, I may make appendix videos or streams investigating the climates of the other subcontinents and update the world map accordingly. Since the Speculative Atlas is focused on Arukia, I wanted to dedicate more time to the subcontinent, and the lower resolution world map allowed me to move through those steps relatively quickly. Once I finished the G-Plates run, I built the topography from the final output. You'll notice that these early drafts don't include the ice sheets. I added those later once I'd done my first pass of temperature mapping. Once I was happy with my land masses, I quickly mapped out the continentality, which I did here on Procreate on an iPad. This is the first step of the manual temperature mapping method that I developed for Artifexian's World Builders log. The temperature guide spans episodes 33 to 35. I'll link the playlist and the Google Doc in the description. I want to highlight that this guide is specifically for Earth-like planets. I recommend doing continentality first because the zone with the highest continentality on a landmass is going to see high pressure areas form in the mid or high latitudes during the winter, and I find that it helps with mapping atmospheric surface pressure, which is the next step. I do a rough draft of the surface pressure and winds in January and July to get an idea of the currents and precipitation, since both are driven by surface winds. Outlining the steps for mapping pressure, winds, and precipitation is beyond the current scope of the video. It's something I'd save for an appendix if there's interest further down the line. The stage is now set for the second and third steps in the manual temperature guide, which roughly aligns with episodes 34 and 35. I mocked up the isotherms in the iPad first before importing the draft to Photoshop and creating the final temperature maps. Once I finished the average temperature maps for January and July, I added the ice sheets to the topography map. Then I returned to the surface pressure and wind maps to make adjustments based on where the thermal equator landed, the extent of the sea ice in winter and summer, and the equatorward advance of the ice sheet. And finally, I mapped the climate, which more or less follows Artifactian's guide in the Worldbuilder's log from episode 36 to 40 that I consulted for. The major difference is that my precipitation method, as I mentioned above, is different than the dry, wet, very wet scale that was adopted from Worldbuilding Pasta's method. For those wanting a bit more detail, adding low-pressure cyclones to direct winds in addition to high-pressure anticyclones is an extra step on top of the Apple Pie for Scratch guide that can provide some different outputs, but the base method works quite well. And there you have it. These are the steps that I followed from ideation to the global Köppen-Geiger climate classification map. To build Dove's colder climate regime, I needed to settle on a starting average temperature for the 40-degree latitude isotherm, as per the climate guide, and to do that I had to decide how cold I wanted the planet to be. For context, the pre-industrial average is around 13.6 degrees Celsius, but anything between 13 and 14 degrees Celsius should work for that kind of climate regime. This range of average global temperature is quite common for world building, especially fantasy settings based on pre-industrial Earth. Just for a comparison, in 2024, which was the last year at the time of recording, it was 1.55 degrees Celsius above the pre-industrial average, or just over 15 degrees Celsius. The global average temperature during the LGM has been estimated to between 4.5 and 1.6 degrees cooler than the pre-industrial average, or a global average temperature between 7.5 and 9 degrees Celsius. However, if we want a colder climate regime, we can't just lower the temperature of the whole world equally. For Earth-like obliquities, higher latitudes cool more significantly than lower latitudes. The tropics receive pretty consistent sunlight throughout the year, so they don't cool as drastically as the poles. This map demonstrates the difference in average annual temperature from the pre-industrial average. We can see a minor difference in the tropics, between 1 and 5 degrees Celsius cooler, but in the northern polar circle and over glaciers, temperatures were over 14 degrees cooler. Land influenced by cold currents tend to cool more than those impacted by warm currents. And areas further in the interior and near glaciers are also relatively cooler than the pre-industrial average. For the first pass of the manual temperature method, I chose 12 degrees Celsius for my starting isotherm at 40 degrees latitude. Then I went about applying the temperature guide as written. After that, I added in my ice sheets and extended them down to the same latitude over land as the 12 degrees isotherm over the ocean during the summer. And this is because ice sheets have a higher albedo than the adjacent ground cover, reflecting more sunlight. As the glaciers grow, the surface air temperature a meter or two above the glacier is significantly cooler due to the evaporation and sublimation of the ice. This allows the glaciers to continue to expand and grow, as long as cool or cooling conditions persist with enough moisture for the glaciers to advance. This relative temperature difference due to the high albedo of the ice sheet and the relatively lower albedo of the adjacent ground cover creates a low-pressure trough. This low-pressure trough brings precipitation from nearby ocean water and can be very effective, especially when there's a significant relative difference in temperature between the ice sheet and the water closer to the equator, like between the Laurentide ice sheet and the Gulf of Mexico. These dynamics are reflected on Dove in the northern hemisphere. This can also account for the strength of the monsoons in western and eastern Basara. Because we have the significant difference between the warmth of the equatorial oceans, specifically the Agathis Sea, and the expansive frigid ice fields in the equatorial mountain ranges. To account for cooler regional temperatures on colder worlds, there are a few modifications you could adopt for the manual temperature mapping method. The first is to steepen the temperature shift of the base isotherms from the 40 degrees starting latitude to the pole, from 0.7 degrees Celsius per degree of latitude to 0.8 or 0.9 per degree of latitude. This steeper temperature gradient will make higher latitudes much colder. The second is to lower the temperature of cold spots, especially cool current cold spots, even those in the tropics, by a few degrees. And the third recommendation is to shift winter isotherms impacted by cold spots further equatorward. It's worth experimenting and seeing which of these modifications produce the effect you're looking for. Aridity is a concept I wanted to discuss because it's not as straightforward as it seems to distinguish what a humid or wet climate is from a dry or an arid one, depending on how you conceive of aridity. A simple way to judge aridity is to compare the amount of precipitation a place receives. To illustrate this, I'm going to have a little demonstration to see which city receives more precipitation, London, England, or Ouagadougou, Burkina Faso. London is 51 degrees north and 0 degrees west with a CFB climate, while Ouagadougou is 12 degrees north and 1 degree west with a BSH climate. Now you can pause the video here and guess which city receives more precipitation in the comments. London receives an average total precipitation of 615 millimeters, while Ouagadougou receives an average total precipitation of 812 millimeters. Congratulations to everyone who guessed Ouagadougou. What makes London humid and Ouagadougou arid is not just the amount of precipitation, but also the annual daily mean temperature, which is 11.7 degrees Celsius in London and 28.9 degrees Celsius in Ouagadougou. The Köppen-Geiger climate classification uses thresholds to separate B-class climates from A, C, and D climates based on the relationship between temperature and precipitation. Since over 70% of Ouagadougou's precipitation occurs in the 6 months where it receives the most insolation, or the summer, we use this chart. We can plot Ouagadougou's annual temperature and precipitation to see that it falls on the BSH side of the threshold between semi-arid and humid climates. We can do the same for London on a chart for climates that have even precipitation throughout the year. And by doing that, we find that the rainy city falls well on the humid side. Precipitation is an important factor, but what this exercise demonstrates is that other factors are vital to consider when thinking about aridity. The Köppen-Geiger climate classification uses temperature as a proxy for potential evapotranspiration, since higher temperatures cause increased evaporation and cause plants to transpire more. So there's a common misconception that glacial periods are necessarily more arid than interglacials. It's usually said that water is quote-unquote locked up in the ice sheets. However, this doesn't really work out because precipitation originates from evaporated ocean water. Water locked up in glaciers on land does decrease sea level, which changes coastlines by as much as 200 kilometers during the last glacial maximum. And this increases the distance moisture has to travel into the interior, which increases aridity deeper into the landmass. But the drop in sea level does not significantly decrease the surface area of the ocean, which we can see in the figure here. We can see that some changes are noticeable, especially around Sahul and Sundaland, but the surface area of the Atlantic, the Pacific, and Indian Oceans are largely unaffected by this slight increase in land area. One thing you may notice is that higher latitudes are covered in sea ice, and when you have sea ice all year round, you're not going to have much moisture from those areas. There are also some other indicators of aridity that we need to discuss, like pollen samples, which are often used to suggest more arid conditions during the last glacial maximum. Pollen samples from the LGM tend to show more expansive grasslands, which aligns with biomes in more arid climates today. However, when we're thinking about paleoclimate, we also need to consider lower atmospheric CO2 levels. CO2 levels are much lower during the LGM, and when that happens, plants with physiologies that require less CO2 are more successful, which include sedges and grasses. Meanwhile, woody plants, like most trees, rely on more CO2 and don't tend to do as well. However, these plants can still thrive if there's enough moisture from precipitation or surface water. This leads to more grasslands and mixed ecoregions like forest steppe in climate zones that would support forests with CO2 levels more similar to modern Earth. In addition to the impact of CO2, cooler global average temperatures also means that there's less evaporation. The decrease in ocean evaporation causes less global precipitation. However, this is equally true over land. In addition, plants release water to cool down in a process known as transpiration, and cooler temperatures cause plants to transpire less. The decrease of evapotranspiration leads to wetter soils, as we can see in Figure 34, which demonstrates that topsoil moisture increased in some areas during the last glacial maximum, even though some of those areas received less precipitation. One of the main takeaways from Footnote 3 is that systems of climate classification are not biome classifications. The Köppen-Geiger climate classification system was developed to describe climates as they correlated to vegetation on Earth during the late 19th century. So biomes we see in those climate areas may not correlate to warmer or cooler worlds. As an example, we can look to the interior of low-latitude Lanea in the northern hemisphere, where we can see wet summer, dry winter, AW and CWA climates. The relatively warm temperatures of the tropical Agassiz Sea causes a good deal of evaporation that southeasterly winds carry deep into the interior, while the average temperature over land tends to be a few degrees cooler, leading to less evapotranspiration and wetter soils, which prevents a significant spread of the arid and semi-arid climates from the north. The topography also rises from the southeastern coast towards the Urzetegis, forcing warm, moist masses of air to cool, condensing air and precipitating onto the eastern slopes. Thinking back to our London Ouagadougou demonstration, we can actually check the climate here. The annual daily mean temperatures at the X in the north is slightly higher than 18 degrees Celsius, with warm summers averaging near 24 degrees Celsius and cool winters above 12 degrees Celsius, while the plus in the south is 19.5 degrees Celsius on average and has a range between 18 degrees Celsius in the winter and 21 degrees Celsius in the summer. The white line shows the threshold of 600 millimeters in total annual precipitation for the X to transition from CWA to BSH, which happens a little bit further to the north as summer temperatures rise and precipitation gradually decreases. On contemporary Earth, we would likely see mixed temperate forests in the CWA region. However, due to the decreased atmospheric CO2 on Dove, this CWA interior is likely to see encroaching desertification in the north, and a mosaic of xeric shrublands and grasslands, or the Dovian equivalent of grass, in dry forests. These sorts of biomes may correlate better with those in more arid climate classes on modern Earth. To end off this footnote, I've broken down some of the considerations to account for on cooler and warmer worlds. Cooler worlds can expect less extreme latitudinal movement of the intertropical convergence zone. On the other hand, for warmer worlds, the ITCZ can be more dramatic, which leads to regional dynamics like the African humid period, where due to precession, the ITCZ rose higher over the Sahara and caused what are normally xeric biomes to transform into savannas. Colder worlds may see greater cooling of equatorward currents, especially if they're near freshwater glaciers that extend into the ocean, or near the cooler poles, causing less precipitation along the coasts adjacent to those currents. Warmer worlds are going to have warmer polar waters, and this can lead to warmer cool currents and cause more precipitation along those coasts. On cooler worlds, global precipitation decreases, but the impacts are regional, as we discussed. On warmer worlds, global precipitation increases overall due to increased evaporation of ocean water, especially at higher latitudes. However, cooler worlds also have lower rates of evapotranspiration, which will lead to wetter soils. Likewise, hotter worlds have higher rates of evapotranspiration, so the aridity of continental interiors can significantly increase. And finally, colder worlds have a decrease in atmospheric CO2, which is going to lead to different kinds of biomes, like we talked about earlier. The inverse is true on warmer worlds, where atmospheric CO2 is higher, which will allow different kinds of biomes to exist, including forests at higher latitudes. However, plants as we know them may also struggle to photosynthesize if temperatures rise too much. Different kinds of plants have ideal temperature ranges to consider, and higher temperatures may be too hostile for photosynthesis to occur. Thank you for staying until the end of the video. I want to give a shout out to my first patrons, Thanasis and Madeline, for their support. In the next chapter of the Speculative Atlas, we'll return to Urrutia to explore the wet winter savanna and survey the creatures that call this unique Dovian biogeographical region home.